Let us see second example of how to sketch an equation on a Cartesian space. Recall, we've seen this table before. We also recall that this equation, y is equal to 5x minus 2, was what we got by hypothesis from this table. Let us use this Cartesian plane to sketch this table. In other words, let us use this space to sketch this equation. We're going to proceed in a like manner. Don't forget all the things we learned in the first instance. Just the same steps we followed before, we're going to follow in this. Let us see how we go about it. As before, I choose to write this 28 at any point along this line. Look at the 28 written here at this point. 28 is the highest value on the y column. Similarly, we write this 6 along the x-axis. See the 6 here. 6 is written at this point. So what do we have to do? As usual, let us start with this x. That is, let us divide this x-axis into regular intervals, each interval corresponding to a particular value of the x. How is it to be done? I can choose to divide from this point to this point into any specified number of intervals. If I want it to be 2 intervals alone, it means that each interval will correspond to 3 units. If I must break it into 3 intervals, it means that each interval will be equal to 2 units. But I want to divide from here to here into 6 intervals. That means that each interval will be equal to 1 unit. Now watch as I calibrate this axis according to this decision. Clearly we see that line has been broken into 6 equal divisions. That is 6 equal intervals. From here to here is an interval. From here to here is also an interval. And as I said earlier, each interval corresponds to 1 unit. From here to here, 1. From here to here, 1. Which means that from here to here is 2. Then from here to here is 1. Here to here is 1. That means that from here to here is 3. Therefore, that is the way it runs until 6 at this point. Let's do the same thing in case of the y-axis. Let's see. In the case of y-axis, this point is labeled or written, or this point is marked as 28, corresponding to this highest value of y. Don't forget that it is never compulsory that what is written here is this highest point. It is either this highest point, this highest value, or anything above it, but not far above it. In this case, I found it convenient to use this 28 being the highest value of y to mark this point. In practice, you too will see the convenience involved. From this point to this point is 28. So it is up to me to divide from this point to this point into any number of specified intervals. If I want it to be 2 intervals alone, that will be from here to here, 14. From here to here, another 14. Everything making 28. I can decide to divide it into 14 intervals so that each interval will correspond to 2 units. That will give us 2, 4, 6, 8, 10. In that manner, up to 28. But I have decided to divide this space into 7 so that each interval will correspond to 4 units. That is, break this gap from here to here. If from here to here is 28, and I break it into 7, I'll get each of the 7 divisions corresponding to 4 units. I repeat, if I divide from this point to this point, which is 28 units, if I divide it into 7 different intervals, each interval will be equal to 4. Let us see how this goes. That is it. From here to here is 4 units. From here to here, 4 units. That means from 4, the next 4 we make it 8. The next 4 we make it 12. The next 4 we make it 16. The next 4 we make it 20. The next 4 we make it 24. And the next 4 we make it 28. This is the calibration of that axis. But we're going to see a need to calibrate this axis that runs from 0 downwards, vertically downwards along the y-axis. Let us see. Now look at that part calibrated, but briefly, that is -4. As you can see, this position is -4. The gap from here to here is the same gap from here to here. From here to here is +4, but from here to here is -4. The same gap is from this -4 to -8, and that's how it keeps going down. For some special reasons, which we see later, I had to calibrate this -y. Not because there is a -y in the table, but as we have it in projections, based on this formula we got before, we might need this place for intercept. Let's continue. Next, let us locate the values of x as they are found in this table on this x-axis. This is 2. 2 is here. This is 3. 3 is here. This is 4. 4 is here. In fact, everything here is on this axis. That means there is no problem, not too much trouble, locating the tabular values on this axis. What about this y-axis? 8 is here. We can see it. 13 is here in this table. It is no place to be found written on this axis. What we have is 12. We know that there is a place that this 13 is located, but it is not indicated in calibration. Then it means we have to locate it. We know that it is somewhere between 12 and 16. Let us see how to go about it. But before then, let's see other values with view to finding out if they exist written on the axis or not. This 18 is in the table. It is not written on the axis. It exists somewhere between 16 and 20. Where exactly is it located? Later, we find out. In the table, in the column of y, we have 23. That is nothing like that on the axis, but it is somewhere between 20 and 24. What about 28? It is here. That means that it is only 8 and 28 that were found written on this axis. Let us try to estimate. Let us try to get the approximate positions of 13, 18, and 23 along this axis. This 13 is approximately located here, just a short distance after 12. This may not be accurate. We got it by estimation. This 18 is somewhere between 16 and 20. It is just midway between them. This is why this point corresponds to this 18. It may not be accurate, Again, it was found by approximation. 23 is somewhere between 20 and 24. It is above halfway between them. See it here. This is estimated to be the position of 23. And of course, 28 is here. The next is to connect these values so we obtain these partial points of intersection as before. Let's make progress. We go back to our table. This 2 for x corresponds to 8 for y. That means we locate 2 for the x and locate 8 for the y. This is 2 for the x and this is 8 for the y. It means that, like before, this 8 and this 2 we meet somewhere in space. Let us see where they meet in space. They are partial points of intersection. This is where 2 met 8. Let's do a similar thing for the remaining values or pairs of values. All right, these are the other remaining points of intersection, partial points of intersection. You observe that these 2 corresponds to 8. Also, these 3 corresponds to 13. This 4 corresponds to 18. This 5 corresponds to 23. And this 6 corresponds to 28. These are the partial points of intersection among these pairs of values. The next thing is for us to run a line of best fit as before. Let us see how we go about it. All right, that is the line of best fit. Again, what a beautiful line of best fit. It connects all of them. Anyway, if these values were gotten by experiment, it will be difficult to see this line of best fit cutting across all the points of intersection. But because perhaps this was gotten by calculation, line of best fit passed through all of them. Now that we have seen a summary, this summarizes only what happens in the case of 5 pairs of values. But again, you can ask yourself, if 2 corresponds to 8 and 3 corresponds to 13, as we can see here, what about something between 2 and 3, or even something before 2? Take, for instance, what if x were to be 1? With this line of best fit, we can give more information about the behavior of these values corresponding to x and y. If, for instance, the value of x is 1, how do we know the corresponding value of y? As before, draw a line vertically upwards from 1, and then when it meets this line of best fit, turn angle 90 and then go towards the y-axis. What do you meet there? We meet something like 4, or approximately 4. It therefore means that if 2 corresponds to 8, 1 will correspond to 4. What about something like 2.5? That is 2.5, somewhere here. The same seems to be done. Draw a line vertically upwards until it meets the line of best fit. Turn angle 90, and then whatever you meet here is probably the value of the y corresponding to 8. The same thing should be done if the value of y is known, and with 8 we want to get the value of x. In that case, the process is the same. Take, for instance, if we want to know the value corresponding to 26, if the value of y is 26, which is somewhere here, and you want to know the value of y, the value of x corresponding to this value of y, which is 26, what do? Draw a line like this horizontally to meet this line of best fit. Whatever it meets it, draw it down. Whatever it meets the x, then you know exactly the value of x at that point where it meets it. This is a beautiful way of expanding the usefulness of a table. A sketch like this is an important tool towards expanding the use of a table in making predictions. After this, we wish to make effort to see another example, probably to bring out another important point regarding sketching equations on Cartesian spaces.